morning to all. I am A.D.M.COLLEGE, Assistant Professor of Chemistry, A.D.M.COLLEGE for Women, Autonomous, Nagapattinam. I am going to present my topic on semiconductors. This topic present in that BSc Chemistry. Okay, let us see that semiconductor. A semiconductor is a substance that has specific electrical properties that enable it to serve as a foundation for computers and other electronic devices. It is typically a solid chemical element or compound that conducts electricity under certain conditions but not others. Semiconductors are solid that are insulated at absolute zero but which is conduct electricity by the passage of electrons at normal temperatures. Semiconductors are materials whose electronic properties are intermediate between those of metal and insulators. They have conductivities in a range of 10 power minus 4 to 10 power plus 4 second per meter. The interesting feature about semiconductor is that they are bipolar and the current is transported by two charge carrier of opposite sign. These intermediate properties are determined by first one crystal structure bonding characteristics, second one electronic energy bands. The silicon and the germanium are elemental semiconductors and they have 4 valence electrons which are distributed among the outermost s and b orbitals. These outermost s and b orbitals of semiconductors involve in sp3 hybridization. This sp3 hybridization from 4 covalent bonds of equal angular separation leading to a tetrahedral arrangement of atoms in space result tetrahedral shape. Resulting crystal structure is known as diamond cubic crystal structure. Due to the role in the fabrication of electronic devices, semiconductors are an important part of our lives. Now imagine life without electronic devices. There would be no radios, no TVs, no computers, no video cams, and poor medical diagnostic equipment. Although many electronic devices could be made using vacuum tube technology. The developments in semiconductor technology during the past 50 years have made electronic devices smaller, faster, and more reliable things for a minute of all the encounters you have with the electronic devices. How many of the following have you seen or used in the last 24 hours? Each has important components that have been manufactured with electronic materials. Semiconductors are mainly two types. First one is intrinsic semiconductor, second one is extrinsic semiconductor. The intrinsic semiconductor is also known as pure semiconductor. The extrinsic semiconductor also known as impure semiconductor. First one is intrinsic semiconductor. It is also pure semiconductor. A semiconductor which does not have any kind of impurities behaves as an insulator at 0 Kelvin and it behaves as a conductor at a higher temperature in known as intrinsic semiconductor or pure semiconductor. The germanium and the silicon are the most common practical example. The atoms of both have 4 electrons in the outer shell of the atoms and they form the 4 bonds to the other atom and give rise to a tetrahedral structure like diamond. When sufficient energy is given, some of the covalent bonds break. Electrons are ejected from the normal sides. These electrons then migrate, leaving behind a positive charge where a bond is missing. And the electrical conduction takes place by the migration of electrons in one direction. The positive poles migrate in the other direction. This is called intrinsic conduction. Intrinsic semiconductor generally consists of covalent crystal. They may be elements or compounds. Unlike normal metallic conductors, the conduction of a semiconductor increases with the rise in temperature and the presence of impurities. So they do not conduct current at low temperature. Forbidden energy bond. This is because a rise in temperature will create more carriers as more bonds are broken by the thermal energy. Semiconductors have an energy band structure in which the filled valency bond is separated from the empty conduction band. It is a insulator or also having a similar structure. The space between the filled valency band and the empty conduction band is known as forbidden energy band. The forbidden energy band is semiconductor is much narrow than the haze of insulator. At low temperature, the thermal energy of the electrons in the valency band is much too low. So these electrons do not cross the forbidden energy band. So they will exhibit very low conductivity at this temperature. When the temperature is raised, the thermal energy of the electron increases. Some valency electrons have overcome the relatively narrow forbidden band and reach the conduction band. And this when a electrical field is applied. These few electrons are free to flow through the crystal. And this when the electrical field is applied, these few electrons are free to flow through the crystal. Thus, they exhibit a limited electrical conduction at the higher temperature. Further increases in temperature will be increases the number of electrons in the conduction band. The result in increases electrical conduction. At the same time, the unfilled levels in the valency band will also increases conduction of the crystal by the movement of electrons into the now vacant energy levels in the valency band. This is the type of conduction is due to the movement of valencies or holes under the influence of the electrical field. So, semiconductors which consists of atoms of a single type, example silicon and germanium, and which depend for the semiconductivity of the electrons, which is a thermally excited across the forbidden band, are known as intrinsic conduction. Carrier concentration in intrinsic semiconductor. When a suitable for energy is applied to a semiconductor, then electron take transition from valency band to conduction band. Hence, a free electron in conduction band and simultaneously free hole in valency band is formed. This phenomenon is known as electron hole pair generation. In intrinsic semiconductor, the number of conduction electrons will be equal to the number of vacant sites or holes in the valency band. Extrinsic semiconductor. The extrinsic semiconductor are those in which impurities of large quantity are present. Usually, the impurities can be either third group element or fifth group element. Based on the impurities present in the extrinsic semiconductor, they are classified into the two categories. First one is N-type semiconductor, second one is P-type semiconductor. N-type semiconductor. Germanium and silicon belong to group 4th of the periodic table. These elements in pure state have very low electrical conductivity. However, on adding even trace of the element belonging to the third or fifth of electrical conductivity is greatly enhanced. Usually, the impurities atoms are introduced by adding a known amount of impurity to the melt of the pure metal and the crystal is allowed to grow. Alternatively, the important of impurities can be diffused into the pure semiconductor crystal. This is any N-type semiconductor because when a pentavalent element such as phosphorus, arsenic or antimony is added to the intrinsic semiconductor, 4 electrons are involved in covalent bonding. When 4 neighboring pure semiconductor atoms, the 5th electron is weakly bound to the parent atom, and even for lesser thermal energy, it is released, leaving on the parent atom positively ionized. In the intrinsic semiconductor, doped with pentavalent impurities are called N-type semiconductors. The energy level is 5th electron is called donor level. The donor level is close to the water conduction band. Most of the donor level electrons are excited into the conduction band at room temperature and become the majority charge carrier. Hence, N-type semiconductor, electrons are majority carriers and holes are minority carriers. The carrier concentration in N-type semiconductor. Consider niobium is the donor concentration. For example, the number of donor atoms per unit volume of the material and ED is the donor of energy level. This is energy level diagram of N-type semiconductor. At a very low temperature, all donor levels are filled with the electrons. With increases of temperature, more and more donor atoms get ionized and density of the electrons in the conduction band increased. The variation of Fermi level with temperature. To start with the increases of temperature, EF increases slightly. As the temperature is increased, more donor atoms are increased. Further, increases in the temperature results in the generation of electron-hole pairs due to spreading of covalent bond and the material tend to behave in an intrinsic manner. The Fermi level gradually moves towards the intrinsic Fermi level, this is EI. The P-type semiconductor. When a trivalent element such as aluminium, gallium or indium have 3 electrons in their outermost orbital added to the intrinsic semiconductor. All the 3 electrons of indium are engaged in covalent bonding with the 3 neighboring silicon atoms. Indium needs one more electron to complete this band. This electron may be supplied by silicon, thereby creating a vacant electron site or holes on the semiconductor atom. Indium accepts one extra electron. The energy level of impurity atom is called acceptor level, and it is the acceptor level lies just above the valency band. The formation of P-type extrinsic semiconductors. These type of trivalent impurities are called acceptor impurities, and the semiconductor doping the acceptor impurities are called P-type semiconductor. P-type semiconductor band energy. Even at relatively low temperatures, these acceptor atoms get ionized, taking electrons from valency band, this giving the rise to holes in the valency band for conduction. Due to ionization of acceptor atoms, only holes and a number of electrons are created. And these holes are moving number of electrons, and hence holes are majority carriers and the electrons are minority carriers on P-type semiconductor. The both N and P-type semiconductor are electrically neutral. This is because each atom of the added impurity is a neutron itself of conducting equal number of protons and electrons. The conductivity of semiconductor increases with a rise in temperature. In this, they differ from metal in which conductivity decreases with a rise in temperature. NP junction. And this is to the fact that the extra electron or the positive holes is bound weakly to the crystal lattice. So when heat energy is supplied, they are freed from the crystal lattice and thus conduct the current more freely. The combination of N and P types of conductor is known as NP junction. In a semiconductor, the NP junction is created by the method of doping, and the P side of the positive side of the semiconductor has the excess of holes, and the N side or negative side has the excess of electrons. The process of doping is explained in feature details in the next section. Formation of NP junction. As we know, if you use different semiconductor material to make a NP junction, there will be crane boundary that would inhibit the movement of electrons from one side to the other by scattering the electrons and holes, and thus we use the process of doping. We will understand the process of doping with the help of this example. Let us consider a thin P-type silicon semiconductor sheet. If we added a small amount of pentavalent impurity to this, a part of P-type silica will get converted to N-type silicon. This sheet will now contain both the P region and the N-type region and the junction between the two regions. The process that follows after forming a NP junction are two types, diffusion and trip. There is a difference in the concentration of holes and electrons at the two sides of a junction. The holes from the P side diffuse to the N side, and the electrons from the N side diffuse to the P side. These give rise to diffusion current across the junction, and these are used in the manufacture of transistor. NP junctions conduct electric current easily and in the one direction only. So it is used as a rectifier to the change alternation current. AC into the direct and DC. A schematic representative of a semiconductor acting as a rectifier. This is diagram of NB junction. When a external voltage is applied in such a way as a cause motion of electrons the N current, from left and motion of positive holes T current, from left to right, current is steadily conducted if the direction of the voltage is reversed. A separation of electrons and positive holes takes place. There is a cancellation of N and P type current. The conduction stops the NP junction permit the current from the outer side source to flow into the direction only. And the NP junction allows current to flow through when N side is positive with respect to N side. It is said to the forward passes. A PNP or NPN junction can be constructed. Such as the transistors are widely used in radio and electrical circuits. The forward bias of the NB junction. This is forward bias of NB junction diagram. When the P type is connected to the battery positive terminal and the N type to the negative terminal, and then the NB junction is said to be forward biased. When NB junction is forward biased, the filled-in electrical field at the NB junction and the applied electrical field are in positive and the opposite direction. When both electrical field add up, and the resultant electric field has a magnitude lesser than the field of electrical field. This result is a less resistive and the thinner depletion region. The depletion region's resistance becomes negligible when the applied voltage is larger. In silicon, at the voltage of 0.6 voltage, the resistance of the depletion region becomes completely negligible and the current flow across depleted. The reverse bias of NB junction. When the P type connected in the battery negative terminal and the N type connected to the positive side, the PN junction is reversed biased. In this case, the building electric field and the applied electrical field are in the same direction. When the two fields are added, the resultant electrical field in the same directions as the building electrical field, creating more resistive. In the thicker depletion region, and the depletion region becomes more resistive and thicker if the applied voltage becomes larger. Unbiased. This is unbiased NB junction. Also, when the electron diffuses from the N side to the P side, an ionized donor is left vacant on the N side, which is immobile. And as the process goes on, a layer of positive charge is developed on the N side of the junction. Similarly, when a hole goes from the P side to the N side, an ionized acceptor is left behind on the B side, resulting in the formation of a layer of negative charges in the P side of the junction. This region of positive charges of negative charge on either side of the junction is termed as the depletion region. Due to the positive space charge region on the either side of the junction on electrical field. It is the direction from the positive charge towards the negative charge is developed. Due to this electrical field, an electron on the P side, positive side of the junction moves to the negative side of the junction. This motion is termed the drift. Here we see that the direction of the drift current is opposite to that of the diffusion current. The biasing condition for NB junction diodes. And there are two operating regions in the NB junction diode. One is a P type, second one is a N type. And there is three biasing conditions for the NB junction diode, and this is based on the voltage applied. First one is a zero bias. no electrical voltage is applied to the NB junction diode. The forward bias, the positive terminal of the voltage potential is conducted to the P-type, while the negative terminal is conducted to the N-type. Bias, the negative terminal of the voltage potential is connected to the positive diode and the positive is connected to the negative type. NB junction formula, this is important one, this formula, and the formula used in the NB junction depends upon the filled in the potential difference created by the electrical field is given as E naught equal to Vd ln Nt dot into Na by Ni squared, where E naught is the zero bias junction voltage, Vd is the terminal voltage of 26 microfarad at room temperature, Nt and Nu are the impurity concentration, Ni is the intrinsic concentration. How does current flow in the PN junction diode? And the flow of electron from N side towards the P side of the junction takes place when there is the increases in the voltage. Similarly, in the flow of holes from the P side towards the N side of the junction takes place along the increases in the voltage. These result in the concentration gradient between both sides of terminals due to the concentration of gradient formation. Charge carriers will flow from higher concentration regions to lower concentration regions. The moment of charge carriers inside the NP junction is the reason behind the current flow in the circuit. VI characteristics of NP junction diode. VI means V means voltage, I means current, and this is VI characteristics of NP junction diode. This curve between the voltage and current through the circuit. Voltage is taken along the x-axis while the current is taken along the y-axis. The above graph is the VI characteristics curve of the NP junction diode. With the help of the curve, we can understand that there are three regions in which the diode works, and they are zero bias, reversed bias, and then forward bias. When the NP junction diode is the zero bias conditions, there is no external voltage applied, and this means that the potential barrier at the junction does not allow the flow of current. When the NP junction diode is the forward bias condition, the P-type is connected to the positive terminal, while the N-type is connected to the negative terminal of the external voltage. When the diode is arranged in the manner, there is a reduction in the potential barrier. For silicon diodes, when the voltage is 0.7 voltage, and for germanium diodes, when the voltage is 0.3 voltage, the potential barrier decreases and there is a flow of current. When the diode is forward biased, the current increases slowly and the curve obtained is non-linear as the voltage applied to the diode overcomes the potential barrier. Once the diode overcomes the potential barrier, the diode behaves normally and the curve rises sharply as the external voltage increases. The curve obtained is linear. When the PN junction diode is negatively biased conditions, the P-type is connected to the negative terminal while the N-type is connected to the positive terminal of the external voltage. This result in the increases in the potential barrier and the revised saturation current flow in the beginning as majority carriers as present in the junction. When the applied voltage is increased, the minority charges will be increased kinetic energy which affect the majority charges. This is a stage when the diode breaks down. This may be also destroy the diode. Application of PN junction diode. The PN junction diode can be used as the photodiode as the diode is sensitive to the light when the configuration of diode is reverse biased. It can be used as a solar cell. When the diode is forward biased, it can be used in LED lighting application. It is used as rectifier in many electrical circuits and as a voltage controlled oscillator in vector properties. The first one is variable electrical conductivity. Semiconductor in the neutral state, poor conditions because a current requires the flow of electrons, and the semiconductors have the valency band filled, preventing the entire flow the new electrons. Several developed techniques allow semiconducting materials to behave like conducting materials such as doping or gutting. And these modifications have two outcomes. First one, N-type and P-type. These refer to the excess or shortage of electrons respectively. A balanced number of electrons would has a current to flow throughout the material. Heterojunctions. The heterojunction occur when two differently doped semiconducting materials are joined. For example, a conjugation could consist of p-doped and n-doped germanium. This results in an exchange of electrons and holes between the differently doped semiconducting materials. The n-type germanium would have an excess of electrons, and the p-type germanium would have an excess of holes. And the transfer occurs until the equilibrium is reached by the process called recombination, which causes the migrating electrons from the n-type to come to contact with the migrating holes from the p-type. The result of this process is narrow strip of immiscible ions, mobile ions, and which causes an electrical field across the junction. Excited electrons. This is very important. A different in electrical potential on a semiconducting materials would cause a leave thermal equilibrium and create a non-equilibrium saturation situation. And this introduces electrons and holes in the system, and which interact via a process called ambipolar diffusion. Whenever thermal equilibrium is distributed in a semiconducting materials, the number of holes and the electron changes. Such distribution can occur as a result of a temperature difference or photons, which can either the system and create electrons and holes. The process that creates and annihilates electrons and holes are called generation of recombination respectively. The fourth one is light emission. In a creating semiconductor excited electrons and lost by emitting light instead of producing heat. These semiconductors are used in the construction of light emitting diodes and fluorescent quantum dots. The light emitting diode is widely used. Standard sources of light is electrical equipment. It has a wide range of applications ranging from your mobile phone to large advertising billboards, and the mostly find application in devices that show the time and display different types of data. What is LED? The light emitting diode is a semiconductor device that emits light when an electrical current flow through it. When current passes through an LED, the electronic recombination with holes emitting light in the process. LEDs allow the current to flow in the forward direction and blocks the current in the reverse direction. The light emitting diodes are heavily doped p-n junction based on the semiconductor material used as the amount of doping. The LED will emit colored light at a particular spectral wavelength when forward biased. This is the LED figure. An LED in encapsulated with a transparent cover as the emitted light can come out. This is a LED symbol, and the LED symbol is the standard symbol for a diode, with the addition of two small arrows denoting the emission of light. And how does an LED work? When the diode is forward biased, and the minority electrons are sent from positive to negative, while the majority holes from the negative to positive at the junction boundary. The concentration of minority carriers increases. The excess minority carriers at the junction recombine with the majority charge carriers. Uses of LED. LED find application in various fields, including optical communication, alarm and security systems, remote controlled operations, robotics, etc. It finds uses in many areas and becomes of this long lasting capacity, low power requirement and swift response time and fast switching capacities. Below are the few standard LED uses. First one, used for TV backlighting, used in display, used in automotives. Fifth one is a high thermal conductivities. And the semiconductor, when high thermal conductivity can be used for heat dissipation and improving the thermal management of electrons. High thermal conductivities refer to the ability of the material to move heat quickly and efficiently. Materials with high thermal conductivity can transfer heat rapidly from one location to another. They are used in application where fast heat transfer is important, such as in heat exchangers. The diamond is the leading thermal conductivity material and has conductivity values measured 5x higher than copper. And the most manufacturing metal in the United States. Diamond atom are composed of a simple carbon backbone that is an ideal molecular structure for effective heat transfer. Sixth one is thermal energy conversion. The semiconductors have large thermoelectrical electric power factors, making them useful in thermoelectric generation, as well as high thermoelectric figures, as merit making them useful in thermoelectric coolers. Semiconducting diode construction. Silicon or germanium is used as the basic materials for construction a semiconductor diode. One end is doped modified to provide an increases in electron availability compared with the pure silicon or pure germanium. This is the N-type material. The other end is doped to reduce the electron availability under the P-type material. Thus, N-P junction is formed. The overall size is approximately a 1/8 inch tube. This is application and uses of diodes. First one is changing AC current to DC current. And the most basic function would be changes AC current to DC current by removing some part of the signal. This functionality would make them rectifier. They are used as electrical switches and are used in such products because they can prevent a spike in the voltage. Second one is a logic gates. Diodes help in performing digital logic. Millions of diodes are used similar to logic gates and used in modern processors. A logic gate is a device that acts as the building block for digital circuits. They perform basic logical and functions that are fundamental to digital circuits. Most electronic devices we use today will have some from a logic gate in them. For example, logic gate can be used in digital electronics such as smartphones and the tablets or the memory devices. In a circuit, logic gates work based on a combination of digital signals coming from these inputs. Most logic gates have two inputs and one output, and they are based on the algebra. At any given moment, every terminal is in one of the two binary conditions, true or false. False represent 0 and then 2 represent 1. The third one is a carrier wave. This is one carrier wave and they are used in isolating signals from supply. For example, one of the major uses of diodes is the remove negative signals from AC current. This is known as signal demodulation. This function is basically used in radios as a filtering system in order to extract radio signals from the carrier wave. Next, fourth one is a voltage doubler. This is voltage doubler They are also used in creating power supplies and voltage doubler. Using a full wave rectifier will help to deliver a more stable voltage. Combination of diode with a capacitor will help to make small AC voltage multiply to create very high voltage. The fifth one is the LED, light emitting diodes. Light emitting diodes are LED are used in sensor and also in laser devices, many other light illuminating devices. A light emitting diode is a semiconductor device that emits light when a electrical current flow through it. When current passes through an LED, the electron recombination with holes emitting light in the process. The sixth one is Zener diodes. This is one Zener diodes. It is used as voltage regulator, and varactors are used in electronic turning and varistors and used in suppressing AC lines. Zener diodes are semiconductor devices that allow current to flow in both directions, but is specialized in current flowing in reverse. Also known as breakdown diodes, Zener diodes are the most common electronic compounds used as suitable voltage references for electronic circuits. Seventh one is a diodes. This is one diodes. The diodes are the basics of operating amplifiers and transistors. What is diode used for? Diodes can be used as rectifiers, signal limiters, voltage regulators, switches, signal modulators, signal mixers, signal demodulators, and oscillators. The foundation property of a diode is it is a tendency of conduct electric current in only one direction. Thank you.